Right, let's jump into the 2-1 power rule notes here. Usually I have a section before this one to kind of set up just kind of the structure and the overall thinking of what's going on here. But it's a little bit more labor intensive, and it's probably better for an in-person sort of learning environment. So we're just going to take a look at the more procedural aspect of this, and then we're going to go back and give some more context to what this derivative thing is and why this power rule thing is important and all that stuff a little bit later. We'll probably jump into that at some point next week, but I was trying to find a lesson here that hopefully would, strike some previous knowledge to us about functions and how to work with them, as opposed to getting into more of the conceptual sort of stuff. So if you don't understand what a derivative quite is yet, we'll jump into that a little bit more. Just kind of go with it for now. Try to get the procedural aspect of it down, how to actually do the things that we're doing, and then the context will come a little bit later once I'm back in the classroom with you next week. Okay? So we've got a goal problem up at the top, and hopefully you've noticed the word derivative and something that is as maybe something that is a little bit foreign to you. Maybe that's an ugly function for you to look at, but let's just go ahead and jump right in. All right. The power rule, very, very simply, is when we end up with something where we have x to an n power, where n is just a number, right? N is any number that we can come up with. We can do this derivative thing, or take the derivative of something, by taking that exponent power of n and multiplying it by the coefficient out front, keeping the x the same, right? We're not going to touch that x, we're just going to keep that the same. But then we take that exponent and we're going to take it and subtract 1 from it. Okay? And this is just going to become a real procedural thing, hopefully, for us. Okay? So let's do a couple of examples to hopefully kind of drive home the point here. Example A says take the derivative of y when y equals 4x to the third plus 3x squared minus 7x. Okay? Just your everyday run-of-the-mill cubic function. All right? So let's go ahead and apply this power rule thing. The first thing we need to do is do our derivative of y. Okay? And we're going to show that notation as y, and that's a prime. That's not to the first power. Okay? That is y prime. And so just get into the habit of doing that with your derivatives of y, and we'll see it with the f of x and g of x and stuff like that here in a second. But that's a y prime, and we'll talk a little bit more and deepen our knowledge about that as we go forward. All right? But now let's apply the power rule to the other side. Now, we're going to apply this power rule 3 times, okay? And we're going to apply it to those 3 terms, okay? When we have our terms separated by pluses and minus signs, we're going to take the derivative of those individual things separately. All right, so let's apply the power rule, okay? I'm going to go ahead and erase those real quick and just highlight it. I'm going to take that power of 3, just like in our power rule up above, and multiply it by the coefficient out in front of my exponent. So I'm going to take that 3 and multiply it by 12. So 3 and multiply it by 4. 3 multiplied by 4 is 12. Keep that x the same. And then I'm going to subtract 1 from that exponent. The exponent was 3, subtracted 1 is now 2. There's the derivative of our first term, 4x to the third power. All right, let's do the second one. Power is 2, multiplied by the coefficient out front. 2 times 3 is positive 6. Keep the x the same. Subtract 1 from the exponent. It was 2. 2 minus 1 is 1. All right, let's do the last one, minus 7x. Right, it's 7x to the first power, so 1 times negative 7 is negative 7. And if I subtract 1 from this, do you see this becoming x to the 0 power? And anything to the 0 power is 1, so I could put negative 7 times 1, but usually we just put negative 7 there. All right? So we took the derivative of each individual term, 4x to the third, derivative was 12x to the second. 3x to the second is positive 6x. And the derivative of negative 7x to the first was negative 7. All right, let's try it again. Let's do another. We got what, three? Yeah, three examples here. All right, let's take the derivative of now this to the fifth power function. All right, we're again going to do our derivative of y, so y prime. Okay, not y to the first, y prime, right? And again, I've got three separate terms that I'm going to take the derivative of, right? 12x to the fifth, negative 2x to the second, and minus 10. All right, and so let's take each of those exponents and multiply it by their coefficient. So 5 as the exponent multiplied by 12 is 60. X to the 5 minus 1 is 4 power. So 60x to the fourth. 2 in the exponent times negative 2 is negative 4. X to the 2 minus 1 power is just 1, or minus 4x. Now, the derivative of a constant here, any number, minus 10, 15, whatever, is just 0, and here's the reason why. Right, we could put an x to the 0 power there, right? That's technically 1 like we saw up above. And if I was to take that 0 and multiply it by 10, I would end up with 0. And then 0 minus whatever our x would be is still 0. So the power rule is still working with this constant here, but the derivative of all constants are 0. And we'll see why that is in other ways too, as we add more context. Okay? So the derivative for 12x to the fifth minus 2x squared minus 10 is just y prime equals 60x to the fourth minus 4x. All right, let's try C. Let's do one more. All right, first thing we see is that we're getting a little bit new notation. We're getting the prime in there, right, with our f. Okay, so it's just finding the derivative or finding f prime of x. So let's take our derivative here. So we're going to find f prime of x. And we're just going to apply our power rule. And now we've got to do it 1, 2, 3, 4 times, right? I've got 4 separate terms in this one, so I'm going to take 4 power rules for this one. All right, 10 in the exponent times negative 5 is negative 50. X to the 10 minus 1 is now 9th power. Now, this one has a negative exponent, right? This is still an exponent. We can still treat it like we always do with our power rule here. So take now negative 3 times negative 4 to get positive 12. X to the negative 3 minus 1. Negative 3 minus 1, that's negative 4. It's not negative 2, right? Careful there. All right, let's do our third term, 2x to the 1/2 power. 1/2 times 2, 1/2 times 2 over 1, that's 2 over 2, that's just 1, right? So plus 1, x to the, now I've got to subtract 1 from that 1/2 power. Oh my gosh, now we're getting crazy, right? And if I subtract 1, that's like subtracting 2 halves, so 1/2 minus 2 halves, that's a negative 1/2 power. Ooh, that's tricksy. And then the derivative of negative 1 on the end is 0. Now, we kind of stepped up our game a little bit there, right? We took a look at a negative exponent and a fractional exponent there, okay? And notice I did a little bit of work off to the side here to kind of help me be able to think my way through that, okay? If you want to do some of that work off to the side there, by all means, please do so. Now, that derivative, negative 50x to the 9th plus 12x to the negative 4th plus x to the negative 1/2, that's an ugly derivative, but it's perfectly fine. You don't have to try and simplify that yet. Okay? All right, so take a look back at those three. Exponent times coefficient out front, subtract the exponent by 1. All right, for each individual term. All right, see if you can, for number 1, 2, 3, 4, 5, and 6, see if you can do those and put the answers in your formative. I should have that up and ready to go for you.